Hi and Assalamualaikum. Today I want to present about continuity and discontinuity. Usually I want to introduce myself. My name is Nur Ani binti Muhammad Hussein and our team is Muhammad Afiq Aiman bin Suhairi, Nur Masara binti Makno, Rina Arisa binti Yan Amri, and the last one is Nurul Nadira binti Misnan. Definition, continuity and discontinuity. Continuity refers to a property for a function where it can be drawn without any interruption, meaning it meets three conditions. Discontinuity, on the other hand, occurs where any of these conditions fail, leading to various types such as point jump, infinite or oscillatory discontinuities. Type of continuity. A function is continuity at a point if t. Number 1 is fa exits. Number 2, the limit lim as s approaches a, fs exit. Number 3 is the limit lim s approaches a, fs equal fa. If any of these fail, we have discontinuity. Removable discontinuity. A missing point or a hole in the graph condition, the limit lim fs approaches a, fs exits, but fa is missing or defined incorrectly. For example, fs equal x squared minus 1 over x minus 1. They simplify to fs equal x plus 1, except at x equal a, at x equal 1, there is a hole. For graph, a smooth curve but with one point removed. Some discontinuity, the left hand limit and right hand limit exit, but they are not equal. For example, fs equal 1, s less than 2, fs equal 3, s less than 2. X approaches 2 minus fs equal 1, s approaches 2, fs equal 3. These are not equal approaches to jump. For the graph, a sudden jump from one value to another. Infinite discontinuity. Function approaches infinity or negative infinity near a point vertical asymptote. For example, fs equal 1 over s minus 3. At the x equal 3, the function blow up to infinity or negative infinity. For a graph, the graph shoot up or down without bound. Oscillating discontinuity. The function oscillates, keeps switching value infinitely as it approaches a point. For example, fs equals sin 1 over x. As s approaches 0, the function oscillates faster and faster, never settling. For a graph, rapid vibration near the point limit does not exist. Important theorem. Number 1, intermediate value theorem. If a function is continuous on a, b, then must pass through every value between fa and fb. The meaning, a continuous function cannot jump. Number 2, extreme value theorem. If a function is continuous on a closed interval ab, then it has both maximum and minimum value on the interval. It will always reach its heights and low point. Number 3, continuity of composite function. If a g is continuous at a and f is continuous at ga, then the composite function fgs is also continuous at a. In simple word, process if both functions are smooth, their combination is smooth too. Limit continuity theorem. A function is continuous at x equal a if and only if lim ss approaches a, fs equal f, A. This shows that limit and continuity are closely linked. How limit relate to continuity? A function is continuous at a point s equal A if only and if. For example, lim as x approaches A, fx equal fa. They give us three important conditions. First, the function value exists, fa exists, and number two is the limit exists, lim as x approaches A, fx exists, and number three is the equal lim as s approaches A, fx equal fa. If even one of these fail, the function is not continuous at A. Why is the limit important for continuity? Number one, limit describe the behavior of the graph as approaches a point. Number two, continuity requires that the value the function is heading toward meets that actual value of the point. Number three, if the limit and function value don't match, approaches discontinuity occurs. Type discontinuity caused by limit. Number one is jump discontinuity, approaches left limit and right limit. Number two, infinite discontinuity, approaches limit goes to infinity. Number three, removable discontinuity, approaches limit exit but fa missing a wrong value. For example, let fx equal s, find continuity at s equal 3, f3 equal 9, lim ss approaches 3 x square equal 9, the mesh approaches continuous. Not continuous, example, let fs equal x square minus 1 over x minus 1. If x equal 1, function is undefined, approaches f1 does not exist, but the limit lim as x approaches 1, x square minus 1 over x minus 1 equal 2. The limit exists, but f1 does not approaches discontinuous at 1.
So we have three equations for function, which is the firstly is piecewise function, which is we have three equations: fx equal to x plus 2, fx equal to 3, fx equal to x square. So the method in the limit analysis is we has two, the left hand limit and right hand limits. So the equation for left hand limit, limit x plus 2 into x to 1. So we have substitute 1 into x, so we get 3. For the right hand limit, we have limit x square equal to x square plus x square only, and we have substitute 1 into the x, so we get the answer is 1. So for the classification of discontinuity, since 3 is not equal to 1, limit does not match into jump discontinuity. So which is limit x equal to 1, fx is not equal to limit x equal to 1 plus fx. So the continuity or discontinuity proof a function is continuous at x equal to 1 only if limit exists, function value exists, both are equal. Here limit does not exist, which is left is not equal to right, therefore fx is not discontinuities at 1. The graph given is piecewise function with jump at x equal to 1, so we have two lines in the graph. So the next is function, which is rational function. So the equation given fx equal to x squared minus 4 over x minus 2. Simplification, factor the numerator. So we have to simplify the equation to get the answer. So at x equal to 2, the function is undefined division by 0 because we substitute the 2 into the equation and we get a 0. So the limit is a type of discontinuity of rational function, which is limit exists, and the second is function value does not exist at equal to 2. This removal discontinuity a whole. So the continuity or discontinuity proof, which is check the condition if the limit exists, which is yes for the limit. For the second, function value exists, is no. And the lastly is limit equal to function value and cannot check. Thus, fx is not continuous at x equal to 2. The rational function graph, which is that have one lines into the whole, which is 2 and 4.
So for the last of the type function is trigonometric function, which is fx equal tan x. Definition of this function is factor the numerator is tan x equal sin x over cos x. So the function is undefined when the denominator cos x is 0. So points of discontinuity is cos x equal 0 when x equal pi over 2 plus k pi k exponent z. So there's a few of example discontinuities. First is x equal pi over 2. Next, x equal negative pi over 2. And lastly, x equal 3 pi over 2. So next point of discontinuity, which is as x approach any of this value, tan x plus infinite or minus infinite. So there's infinite discontinuities vertical asymptote. So limit proof of trigonometric function, example of x equal pi over 2. Limit as x approach pi over 2 minus tan x equal plus infinite. Limit as x approach pi over 2 plus tan x equal minus infinite. So limits do not exist, which is function not continuous there. So here graph of trigonometric function, graph of y equal tan x showing vertical asymptotes.
Assalamualaikum and good morning. My name is Rina Elisa binti Ya Amri. My metric number is BB10403. Today, I will be discussing a real-world application of this topic by looking at how human body temperatures changes throughout the day. First of all, we need to know that human body temperature changes slightly throughout the day as part of a natural cycle called the circadian rhythm. Generally, it may be lower in the early morning, rise in the afternoon, and then fall again at night. Alright, with that understanding, let's continue by looking at how this function behaves over time. If we let Tt represent body temperatures at time t, the graph of the function forms a smooth curve. The temperature increases and decreases gradually over time without any sudden spikes or drops. This shows that the output changes steadily as time moves forward. Now that we know how it behaves, let's move on to why this function is considered continuous. So, this function is continuous because body temperature does not jump instantly from one value to another. There are no sudden breaks, gaps, or jumps in temperature during normal daily fluctuations. Instead, the temperature changes smoothly and gradually.
Hi, Assalamualaikum. My name is Nurmaisara binti Maknur. My matrix number BB240102. On this slide, we are using a trigonometric function to model body temperature. The function is written as t of t equals 37 plus 0.5 times sine of open bracket 2 pi over 24 close bracket times 3. To find the temperature at t equals 6 hours, we first express it as a limit. The limit as at t approach 6 of t of t. Next, we substitute t with 6. 37 plus 0.5 times sine of open bracket 2 pi over 24 close bracket times 6. Now, we simplify. Inside the sine function, we get pi over 2. And sine of pi over 2 equals 1. So, the final value becomes 37 plus 0.5 times 1 equals 37.5 degrees Celsius. This means that at 6 am, the body temperature is 37.5 degrees Celsius. Since the limit equals the function value, the temperature function is continuous at t equals 6. On this slide, we have a graph showing body temperature measured every 6 hours over a 24-hour period. The data points are 0, 37, 6, 37.5, 12, 37, 18, 36.5, and last 24, 37. This points from a smooth wave-like curve. The temperature rises in the morning, falls slightly in the evening, and returns to normal by 24 hours. There are no jumps or gaps in the graph, which means the function is continuous over the entire day. This shows that trigonometric functions can realistically model natural change in the body temperature over time.
In conclusion, throughout this project, we explored the concept of continuity and discontinuity, studied different types of discontinuities, and looked at important theorems to understand function behavior. We also examined real-life applications such as tracking body temperature, where changes can be continuous or show sudden jumps. Ultimately, this helped us connect mathematical concepts to everyday situations and improve our practical understanding. That's all from us. Thank you.